Okay, we're going to look at a few examples of modeling with linear functions. So keep in mind, all of these are linear functions. We're going to have different situations, and we are coming up with a linear model for those. So here's our first situation. A company sells donuts. They incur a fixed cost of $25,000 for rent, insurance, and other expenses. It costs $25 to produce each donut. So our first question says to write a linear model to represent the cost C of the company as a function of X, the number of donuts produced. So I'm going to call this C of X because I'm told the cost C of the company is a function of X. So you pretty much can get this. Remember, we need a rate of change. And so our rate of change right here, it's 25 cents per donut is how much it costs. So that's our cost per donut. So we're going to have 0.25 times X, since this is our rate of change, plus our fixed cost. So that's it for our linear model. Obviously, you're probably thinking they're not all going to be that easy. And you're right, they're not all going to be that easy. But this is what we're after, some kind of a linear model. So then in part B, I ask you to find and interpret the Y-intercept. Well, the Y-intercept is $25,000. So think about what a Y-intercept means. Well, for any equation, to find the Y-intercept, it's when x equals 0. But you have to put the context to the problem here. So this is the cost, so let me put a dollar sign on it. The cost the company incurs even if they sell 0 donuts. That's a fixed cost. That means it's going to cost this amount no matter what, to pay the rent, the insurance, probably to pay their employees. So even without selling any donuts, it costs that amount. That's what the Y-intercept represents in this problem. The next problem deals with a city's population. It's been growing linearly. Now, later on, we're going to be dealing with exponential functions, and we'll have populations that are growing exponentially. In 2008, the population was 28,200. By 2012, the population was 36,800. Assume this trend continues, which of course is a pretty big assumption, but let's go with it. So we're asked to predict the population in 2018. Well, first I need to come up with a linear model. So that's what we're going to look at first. Now we could use 2008 as our initial year, and we could actually say, using this as a value. But a lot of times, rather than using large numbers like that, I'm going to let X be the number of years since 2008. So I'm using the 2008 as my initial year. So that way in 2008, I can say that's year 0. And the population was 28,200. So 2012 would be 4 years later. So that's going to be a 4 and 36,800. So I need to find, now I have 2 points. So it's linear. And I have 2 points, so I need to find the slope of the line. So we're going to take 36,800 minus 28,200 over 4 minus 0. And we get, let's see, sorry, should have had that written down. We get 8,600 over 4, so we have 2,150. Now remember, this has units. What do these numbers represent? This is our population. So we have people per, and in the denominator we had years. So people per year. So this is the growth rate. It's growing at a population or at a rate of 2,150 people per year. Now I'm not done yet because I have to predict the population. So I need to write my equation. I'm going to call this population, and I'm using x, so P of x. So we know the slope, 2,150, my rate of change, times x, number of years. And because I chose to use year 0 as my population, this population here, I don't have to do anything to solve for the y-intercept. So that's a really nice feature of doing it that way. If I had used 2008, then I'd have to go back and figure out what the population was in year 0, which doesn't necessarily make any sense to the problem anyway. So this is just better to do it that way. So now if I want to know if I want to make a prediction for the year 2018, now don't plug a 2018, you're going to plug in an 18 since that's 18 years since, oh, I take that back. You're going to plug in a 10 since it's 10 years since 2008. So if you substitute that value in, and when you do that, you will get a value of 49,700 people. Okay, so I have my linear model, and I used my linear model to make a prediction. The next part says, identify the year in which the population will reach 54,000. Okay, so I want to know, this time I want to know when is the population 54,000, and I have to figure out the year. So I take my function, and I set it equal to 54,000, and I solve that. So I get, you can just subtract. If you subtract and then divide, you can work this out, trust me. You actually get 12 when you do this, when you solve this. So if you subtract 54,000 minus the 28,200 and then divide by 2,150, but obviously that's not year 12. Remember what x represented, the number of years since 2008. So now you're going to take 2008 plus the 12, and we see it's in 2020, so it would be during that year. Then the last problem, which I've already kind of done, state the slope and interpret the value in the context of the problem. So we're going to do that. Well, I already have that up here. So we had the slope was 2,150. So what this represents is the population is growing. Now it's possible for a population to decline as well. That would show up as a negative rate of change. The population is growing at the rate of 2,150 people per year. And that's actually quite a large growth rate. Probably not going to be sustained for a long period of time, but we were kind of going with that as a basis for the problem. And the last example I want to go over with you is when hired at a new job selling electronics, you are given 2 pay options. Option A is a base salary of $14,000 a year with a commission of 10% of your sales. And option B is a base salary of $19,000 a year with a commission of 4% of your sales. How much electronics would you need to sell for option A to produce a larger income? So, this might not be, like, I doubt that one particular job that you go to is going to give you 2 different pay options based on this, but maybe you're looking at competing job offers and they're based partly on commission, partly on salary. So, being able to do a problem like this could be helpful if you are comparing those 2 different things. So, if we are figuring out for this one, let's say for option A, because we need a model for that. Now you remember that when you are making, actually let's do this. Let's let X equal amount of sales. And we'll let Y equal your income. That would be your salary plus your commission. So for option A, you're going to take 10% of your sales, where your sales we said was X. So this is going to be 0.1 because we have to change that to a decimal value. So 10% of your sales we would represent as 0.1x, 4% of your sales, 0.04x, and then we have this fixed cost that or this fixed salary that you're going to get. So notice that this is a lot like the donut problem. So we would have y equals 0.1x, because that's how much you're going to make from your sales, your commission, plus your salary of $14,000. And for option B, your income would be 0.04x plus $19,000. So the question, when we have to decide when is option A better. Now, one option you could do is you could graph both of these and you could see when the one will overtake the other, and that would be an option. If you remember from Algebra 2, we did some things like this. We could also decide where are they the same. So when would your income be the same? So I'm going to solve that, 0.1x plus 14,000 and 0.04x plus 19,000. And I'm going to solve this so I can figure out when they would be, when the two would produce the same amount. Now you might want to put a 0.10 there just to kind of help you out. So if I subtract 0.04x from both sides and subtract 14,000 from both sides, we get 0.06x equals 5,000. And if you divide both sides by 0.06, you get x equals $83,333.33. So what does that mean? Up until this dollar amount of sales, option B is better. So if you think that you are going to sell, if you sell more than $83,000, let's just say $333 worth of electronics, then at that point, option A is better. Okay, so we create a linear model and then we do something with it. We make some predictions. We look at what different values are. We have to interpret the slope and the y-intercept sometimes in the context of the problem. We might have to put two linear equations together and find out when they're equal. So these are all different things that you'll have to do on the problems, but remember in each situation you are creating a linear model.